Those just a question. You know those scans work?
They do.
Hey, hello everyone. Can someone on Zoom confirm if they can hear me?
Okay. Yeah.
Okay, cool.
Can you also see the screen?
Well, hey, I'll let you know.
So welcome everyone. Welcome to Recitation 5 on CNN Basics and Backpropagation. I'm Ishani and with me I have Uni and we will go through how what is convolutional networks and like the basic forward pass and the backward pass through it. And also we'll go through a notebook which will show all how to use these things, like how to implement these things via PyTorch. Before this, do check Piazza. There's a logistic post on homework 1 part 2. I guess the Piazza post number is 497. Do check it out. Don't miss it. So yeah, let's start. How can I navigate that? Okay, cool. So why this concept of convolution start? Like I guess professor has already started explaining about convolutions and convolution networks, and it starts from an image. And what is an image? Like for us, for humans, the image is basically a visual representation of a concept. But for a computer, it's nothing but just a grid of pixels. So it's basically the whole matrix of like for a black and white image, it's like 2 by 2, it's an n cross m matrix where each and every grid represents one pixel value. So a matrix where ith and jth column represents the intensity of that pixel, and the value can range from 0 to 255, where 0 represents the black and 255 represents the white image. And if we move on to color images, so color images, the number of channels increase. What do we mean by channels here? It's basically the depth of the image. So from earlier we just had one just n cross m matrix. Now we have 3 cross n matrix, where 3 represents the number of channels we have in this image. And here now again that ICIJ, that intensity at pixel ij is for that particular channel C. So before moving on, like I just want to take a quick survey, like how much of a background do you people have on convolutions? Like how do they work? How is it like, how much of you already know? Anything? Or let me put it in a yes or no question. Do you know about like what CNN is? Kind of? Okay, cool, then I can go at a normal pace. Cool. So we know about MLPs right till now. And what MLPs does is that it takes a vector of input, the whole layers, linear layers, activation layers, and you get a vector of output, an output vector. Now, analogous to it, what CNN does is that it takes a map to map. So a feature map as an input and converts that into a output feature map. So how does this help is like, if you can imagine, like if we can do this via MLP as well. But what we have to do is that we have to flatten it, convert it into a single 1D vector and pass it to an MLP. And that will increase the number of parameters on which the MLP needs to be trained. CNN allows you to have shareable parameters and work on the entire 2D feature map itself. So these are the kind of the building blocks of convolution neural networks. We have convolution layers, we have pooling layers, and the hyperparameters. I guess till now you all are familiar with the term hyperparameters because of your part 2s. So in CNNs, when you will do it in your homework 2 part 2, the parameters will be the kernel size, the stride, the number of filters, pooling size type, the padding type, all those things. So let's start with convolution. What is convolution? Convolution is basically nothing but a mathematical form, like it's a element-wise multiplication and element-wise multiplication and summations. So we just, if you see this example, this is a kernel. We can call it a kernel or filter or any, like there are 3 names to it: kernel, filter, or a weight matrix. From image processing, traditional image processing point of view, we call it a kernel or a filter. And weight matrix comes in when we think from a neural network's perspective. So this kernel basically convolves across this image and creates this output image. And if you get, see some intuition of it, it's basically an edge detector. So it's detecting where zeros have just changed to 1. I'll show how this calculation comes in, but the intuition of convolution is basically all of these filters extract a particular feature from an image. So each you can hard code a filter and decide what feature of an image you want to extract. How neural networks help is they learn these filters via forward and via that entire thing of forward pass and back propagation. These kernels are learned by convolution neural networks. So let's go through one by one, go through how this convolution happens. So this convolution, whenever I say filters are convolved across the image, that is represented by this sign of this asterisk sign. This generally represents convolution, and it's going through each and every pixel value. So you put this kernel exactly on top of the image of each and every pixel, do the element-wise multiplication and the summation. So this Z11, if you see in the at below, it's it's doing A11 into W11. So this W11 is multiplied with this, W12 is multiplied with this, and W21 with this, and we add it all, add the bias to it, and then we get Z11. Similarly, we can go through all the pixels and we get this final output map. I'll stop here and ask if this convolution makes sense. Any questions on Zoom? Okay, cool. Yeah.
The bias for every pixel value we have a bias, or how does the bias work?
Bias works, so when you do the final addition, so this here B is added. So like you.
In the figure it says B11.
Yeah.
So we'll have another bias for B12, B13, like that.
So
it's the same bias for the whole matrix.
This you can choose. We can have so generally we have similar bias for for the entire matrix, or you can have bias for corresponding to the weights, 2x2 bias here. So the size of the kernel is 2x2, so you can have a bias also of 2x2.
Okay.
Okay. So this happens, and so if you see here, the input has reduced and the output, the output size have changed. For CNNs, we can calculate what this output size will be, and that is using this formula, wherein the output size is basically the input width minus the kernel size plus 2 into P, where here P represents padding and S represents stride. I'll just in next few slides, you will understand what padding and stride is, and this is added, one is added to it. So I guess you can do a quick calculation to understand where, how this 4x4 input size converted to 3x3 when we did a stride of 1 and padding of 0. So this is the whole quick summary of this convolution neural network, wherein we have an image, we have convolution layers. These convolution layers consist of these different filters which do all these convolution steps which I mentioned before. I mentioned it from the perspective of scanning each and every weight across the image. In the background or in the PyTorch, how it works, it's a complete matrix multiplication, and you can do all these calculations in one go. So it's not exactly scanning one by one. That's the intuition how these things happen. But matrix multiplication allows you to do this in one go. You pass it through an activation layer, and finally, you can get different features. So here, if we tried 4 different filters, we extracted out 4 different types of features from this particular image. Okay. So let's move to stride. As I said earlier, we have been working with stride of 1. Stride represents how much bigger steps you do when you are convolving your filter across the input image. So we can have when we have a stride of 1, we were moving 1 pixel at a time. If that makes sense, that first this this were 1 by 1 stride, I mean, like it will go to A11, then it will go to A12, like consider it from top to top. W11 with A11, then it will go to W11 and A12. When we increase the stride, now the first step will be same, but the second step will be, the W11 next time will be multiplied with 13 directly. So it just moved 2 steps. So, and the stride is symmetrical, like you move 2 steps here and you will move 2 steps down as well. So now the stride, you do the same convolution and you get a smaller matrix output. So what generally it is used for, like you can see here, right? The input image has reduced to now 2 cross 2. So it's generally used for as a concept of downsampling an image, because the whole point of convolutions is many times to reduce the feature map and able to like capture the important features of an image in as much as less metric size as possible, which will help in lesser number of parameters as well. So it's the same thing here. You can interpret stride greater than 1 here. Like when we had a stride 1 output, feel free to do this calculation at your own pace. You will get with stride 1, you will get this output, and with stride 2, you will get an output of this. And this is basically nothing but you are dropping the intermediate layers. And this will be really helpful when you will be doing your homework to part 1, because then you will have to implement this downsampling and upsampling on your own. And how do you drop the intermediates, or like how stride greater than 2 or less than 1, like how stride less than 1 and greater than 1 can achieve both upsampling and downsampling. So think about it, and it will be more like, you'll have to think about it in homework to part 1, but yeah. Okay, next is padding. Sorry, yeah. So before that, any questions on stride? Cool. Next, go to padding. Why do we need padding? Well, you must have observed, or not, I don't know. This top pixel never gets to interact with the bottom weight of the filter. So this W22 never gets to get multiplied with A11 if you don't do padding. And similarly, your last pixel in your image, like the bottom right, doesn't get to interact with this W11 cell of your weight matrix. In order to have this, that like each and every pixel be interacted with each and every value of the kernel, we do padding. Or we can, another intuition behind padding is to preserve the input size. As you must have seen earlier, our 5x5 image got reduced to 3x3. Yeah, 4x4 image got reduced to 3x3. You can maintain the size of your input if you do appropriate padding. Be cautious about it, that sometimes we want to do padding, sometimes we don't want to retain the size of the input. So we have to be cautious when should we use padding or when should we not. So here it's the example of where we are retaining the size of the input image. So we did a padding with like 0 padding across all the sides. Use the same 2x2 filter. And if you do this multiplication, now each and every value of the weight is getting interacted with everything. So now this will also get multiplied with W22 basically. And you will get, and you can again use this formula of calculating the output size. Where is it? Yeah, this one. That when you use a padding of 1, how you can decide what should be the padding value if you want to retain the size. You can just put W out is equal to W in, and you can decide how much padding you need. Okay. So this was the intuition behind padding. Again, moving forward to the more complex part of multi-channels. Any questions? So until now, I just showed you examples on single channels. Any questions? Okay. I either explained too well or it's too much information to digest. Okay. Yeah. Okay, let's go to multi-channels. So what happens when the number of channels increase? These things will be really helpful to understand, like when you do coding or when you want to understand or you manually want to do all these computations on your own with your hand, that the number of kernel channel is equal to the input channels. The channel C of the kernel convolves with the corresponding channel C of the input. That's why the kernel number of channels in the kernel has to be equal to the number of channels in the input. The number of channels in the output, that will be equal to the number of kernels you will use. So why? Let's see. Each and every channel of the kernel convolves with each and every input. It creates an output map, and then you sum all those output maps and create one map. So one kernel creates one output map. So if you want to create multiple channels in your output, you need to increase the number of kernels with which you convolve your input image. Makes sense? It's very important because this is the thing which can affect all, like when debugging your CNN, these are the things will affect, because especially with like as the channels increase, you get lost in these numbers. Yeah.
So the slide kind of makes it seem like the number of channels is not going to change through this CNN. Is that true?
No, so it will change based on the number of kernels. Like in your convolution layer, you decide how many kernels you want to, how many filters or kernels you want to use. So if you use 3 filters in your convolution layer, you will have 3 channels in your output. Your output channels are defined by the number of kernels you used. The number of channels in your kernel, that is defined by your input. No? Okay, one more time. How the channels will change throughout your convolution neural network, that is defined by the number of kernels you will use in each and every convolution layer.
Isn't that set by the number of input channels though?
No. So kernel is basically, again, a n cross m, or like C cross n cross m matrix, right? With that C of kernel, that is defined by the input channel.
Okay.
Now the output, that is C out, comma, weight out, comma, height out, that C out will be equal to the number of channels you have in your, number of filters you have in your convolution layer. Okay, let me show you with an example of, it will make sense with 2 filters. So here you see, we had 2 filters. 2 filters means 2 kernels. Each kernel has 3 channels because our input layer has 3 channels. So each and every channel correspondingly multiplies, and we create an output map as I showed before, and a black and white image. We add that up element wise again, and we create one output map. So this output map, like one filter will create one output map. These output maps will increase. So these basically are the number of channels you are creating in your output. These will increase if you increase the number of kernels. So you can decide that, yeah.
How do you sum all the channels in a particular kernel so that you get one channel as the output?
So this part, so these channels, like there's a, imagine it like depth-wise, you are doing addition across, like.
So you add all the basic elements of that across.
Yeah, element-wise addition across channels.
And right now the output is 3 cross 3 and the kernel is 2 cross 2. So is that something that will happen, or?
That again you can calculate based on your, if a 4 cross 4 input is given with no padding and stride 1, and convolved with 2 cross 2 kernel size, what will be the output? I missed the filter 1, but that's exactly actually what it is doing. That we are multiplying W11, this like color, you can do color mapping as well. Blue part of this channel will be multiplied with the blue channel of this input. And that way you will calculate all the almost output maps and do the addition on this depth and finally get this one final output map. Yeah.
Inside the same kernel, are the weights across the different channels the same?
No. So these things, again, like you initialize a kernel and these things get learned. The
Okay.
network learns these weights. So these weights are different. Any other question?
Yeah. Do we need a C input bias terms for each kernel? Or with just one bias term is enough?
Again, so this is basically, you'll have it like equal to the number of channels you have. You can keep your bias fixed like the way we have, keep it in like in our affine values as well. We have different weights, but we keep bias 1 only, right? And we just add it in the final matrix multiplication, we just add it. And it's like same values added across all the affine values like W into X. So same values added across all this. This is just for consistency. You can change the bias values as well, but it's same. Anything, any question? Yeah.
Is it necessary that my output map for respective kernels should be of the same dimension?
Yes. So, like, it's not necessary as in like you can, in order to, when you say output maps should be same, you mean across kernels, right? If you move, I move
Kernel 1 and kernel
kernel 2, right? So you mean like if you will have different output if you use kernel of different size, right? Right. You can have different outputs, but then that will create a problem. Like in your output, you will have different, like your output layer will have different output sizes. You will either have to manage it by, again, padding it, like when you will concatenating, you will have different output sizes. You'll again pad it, or you'll, because in order to do batch processing, you need everything of same size. So you will again add, like it's increased effort, and also in PyTorch, it doesn't allow you to change the kernel size across, in single layer, across kernels, you can't change the size. If you do, like when you're doing your homework on P1, homework to P1, you can try implement it, you can do all those things, but it's generally not a good practice to do because it adds more overhead. Anything else? Okay, let's move forward. Okay, now we have pooling. So it usually follows a convolution layer and it's used to do like handle the jitter invariance. Invariance, I believe everyone understand. By jitter, it just means that the neighborhood values all might be same, or they might have some variations when we like a new input comes in, like similar image comes in, it just has some variations. So the similar image with just few pixel values here and there, that should not affect the output. So using pooling helps you handle those invariants in a good way, so that the model can understand that both of these two images were same. And it also reduces the memory footprint by reducing the size. I'll show you how it reduces the size. And the general pooling ways are max, mean, or min. You can use pooling any size, like there are many other pooling ways as well. Most usually max or mean is used. And for pooling, until now we saw that the channels change when convolution happens, right? It's dependent on the number of filters. But pooling maintains the channels. Whatever channels was there initially, it's just a processing step on an input, but the channels don't change when you apply pooling. So it's a quick example of max pool, where, quick example of max pool. You do a 2x2 max pooling with a stride of 2. And what max pool is doing is, when you do that convolution step, wherein, so I won't call it convolution, when you put that 2x2 matrix, imagine it as an empty box, put it on the top of an image and get a max of that box, okay? So here, you put that empty box on top of this 2x2 part of the input image, and you get the max, which is 16. Here stride is 2, so you move forward and then take out the 9. Stride greater than 1 makes sense here, like if you use stride less than, like equal to 1 or something, your max value won't have any, like you might end up getting the same image. So you want to use stride greater than 1 when you do pooling. And that's why it reduces the size, and that's why we say that it does like reduces the memory footprint, because the number of parameters now you have to learn has reduced, and it's capturing the max, like whatever things are important in an image. Similarly, what mean pooling does is it calculates the average of it. I mean, you guys can calculate the average. again on the 2x2 part of it. Any questions? Okay, the last part I want to cover is the kernel size. Pooling, we see like, yeah, pooling can reduce the size of the image. And we can use kernel size as well. Till now, I have been just using 2x2 kernel size. You can use different kernel sizes to achieve what kind of output image you want, what size of the output image you want. One, like here, there are two examples using one convolution. So kernel size will define how much of the input the one neuron will see. So this is a 1D example to just help you compare that here the kernel size was 5 and hence this neuron is looking at the 5 pixels in the input. We can use a kernel size of 3x3 2 times and get the same coverage, right? And it's generally preferred to do multiple smaller convolutions than doing one bigger convolution. It helps in your background like matrix multiplication. It reduces the number of parameters as well. And it helps to capture the information in a much more efficient way. Okay. And yeah, like can move to Backprop. Any questions, sorry, on forward before we move to backward? Oh, this question on Zoom.
Okay, wait, sorry. Oh. I think that's been addressed.
Yeah, you addressed it, right?
Yeah, I'm just saying.
For the question is, for the one filter on 3-channel input, is the filter also a 3-channel filter? Yes, and or we are cloning the filter into 3 identical ones. Yeah, so it's a 3-channel filter. All the channels will have different weights, and it might end up learning same weights. That's what neural network would learn, but it's a 3-channel filter if we have a 3-channel input. That is the question. And what's your question?
If you go back to the distributed part of
The kernel size. Yeah.
so you said like the parameters would reduce, right?
Yeah.
I didn't quite get like how is the parameters reducing if you use distributed convolution?
So this will make more sense when Prof will cover these convolutions in lecture, but think of it as why we are not using neural networks. You can imagine neural network is just convolution with a filter of equal to the size of the image, flattened image if you consider. So if we take, basically if you do multiplication with 5x5 versus you do 3x3 and then do 3x3 plus 3, 3x3 plus 3x1. Can you see from the mathematical point of view that doing matrix multiplication of 5x5 will be greater than doing like introducing additions in between, doing it in the form of 3x3 plus 3x1.
Can we move on? Perfect. Okay, so before we move on to the backpropagation with CNN, let's have a little refresher on chain rule, as backpropagation is all about derivation. When we solve for the equations, we move from left to right, which is like the forward pass, and consider the simple computation graph that we have here. After the forward pass, we get an output of f equals -12, right? Now let us do the backward pass. Say, just like in backpropagations, we derive the gradients moving from right to left at each stage. So at the end, we have to get the values of the gradients of our inputs x, y, and z, which is like df by dx, df by dy, and df by dz, right? Differentiating function f in terms of x, y, and z. So working from right to left, at the multiplication gate, we can differentiate f to get the gradients at q and z, which are df by dq and df by dz. And at the add gate, we can differentiate q to get the gradients at x and y, dq by dx and dq by dy. We have to find df by dx and df by dy, but the problem is that we only have got the values of dq by dx and dq by dy. So how do we go about it? So this can be done by using the chain rule of differentiation, by the chain rule, we can define, we can find df by dx as shown in this equation down below here. So we can find the values that we want like this, just like by doing like a simple chain rule, right? This is simple. Now we will move on to CNN. So now imagine a CNN as a massive computational graph. Let us say we have a gate F in that computational graph here with inputs X and Y, which outputs Z. So just like the simple example we just saw, we can easily compute the local gradients, differentiating Z with respect to X and Y as dz by dx and dz by dy. For the forward pass, we move across the CNN, moving through its layers, and at the end we obtain the loss using the loss function, right? And when we start to work the loss backwards, layer across layer, we get the gradient of the loss from the previous layer as dl by dz. And in order for the loss to be propagated to the other gates, we need to find dl by dx and dl by dy. Now let's assume that our function f is convolution between input x and a filter f. Input x is a 3x3 matrix and filter f is 2x2 matrix as shown here. And convolution between input x and filter f will give us an output O. You can see the forward pass here, filter sliding through input x to give you the convolution output. Now coming back to the backpropagation, as mentioned earlier, we get the loss gradient with respect to the output O from the next layer as dl by do during the backward pass. And combining with our previous knowledge using chain rule and backpropagation, we get this computational graph shown here. And we can find the local gradients do by dx and do by df with respect to output O. And with loss gradients from previous layers, dl by do, and using the chain rule again, we can calculate dl by dx and dl by df respectively. Now we come to the question, why do we need to calculate dl by dx and dl by df? So it's because dl by df is used to update the filter f using the learning rate alpha, and dl by dx is the loss gradient from the previous layer. Now let's start with finding the dl by df. We will start off by finding the local gradient do by df, meaning we have to differentiate the output matrix O with filter f. From our convolution operation, we know the values, right? So let us start differentiating the first element O, like O11, with respect to the elements of F, F11, F12, F21, and F22. And let me draw a little bit here because I was confused as well while I was working through this, so hope this helps. So in order to find dl by df, let's first consider our input, which is 3x3. So we have x11 here, x12, x13, x21, x22, x23, so on and so forth, right? And then we will be convoluting this with our filter f, right? Which is f11, f12, f21, and f22, right? And then if we convolve these two together, we'll get an output matrix O, which looks like this, which is again 3x3. But I'll first just consider our output O11, which is done by convoluting this part here with this filter here, right? So we'll be like x11 f11, x12 f12, x21 f21, and x22 f22, right? So this is our output here. And then going back to the slides here, we can see that because O11 equals to x11, f11 plus x12, f12, so on and so forth, finding the derivations with respect to f11, f12, f21, and f22 is same as the equation down below here, which is do11 by df11 is simply just x11, right? This is simple. Makes sense? Okay. And then since O and F are matrices as shown here, and do by df will be a partial derivative of matrix O with respect to matrix F, on top of it, we have to use a chain rule, right? So this does look complicated, but thankfully we can use the formula down below here to expand it. And then if we replace, to substitute the values of the local gradients, do by df from the previous slides, we get much simpler expression like this, right? We just replace do by df with the x, right? So we get this. And then now if we closely look at it, this represents an operation we are quite familiar with, convolution, right? Convolution operation between input x and the loss gradient dl by do, just like shown here. So this is how you find the dl by df, yeah? And then moving on to DL by DO, similar to how we found the local gradients earlier, we can find DO by DX like this. Simple, you know, like we just like replace what we had for DO by DF, which is like f and x, right? And then following our convention, we will use chain rule to find DL by DX. I know it looks nasty, but let me break it down for you here again on the board. So what we are trying to find here is DL by DX, right? We're trying to find DL by DX. And then in order to do so, we have a formula that says we'll do the summation of DL by DOK, DOK by DXI, right? And then in order to find out this part here, wait, let's see. Okay, so this part, sorry. So this one is like same as DL by DO times DO by DX, right? And then we already saw that DO by DX is just same as F whatever, you know, like that's like in our interest, right? So if you think about it, when we expand like this out, DL first, if you want to compute DL by DX11, so I'll just first consider the case for the first row here, input like here. If you first consider DL by DXX, DL by DX12, and DL by DX13, DL by DX11 would be just like same as DL by DO11 times F11, just following our convention here, right? But if you consider the case for DL by DX12, we now have to like think about how these is like convolve to get the output. So if you think about it, DL by DX2, we have to first have DL by DO11 times F11, but we also have to add DL by DO12 times F12 because X12, if you consider it here, this one not only goes through the convolution between like these, but also, I mean, here, corresponding like this part here, it also like overlaps here, right? So it also have the operation that's done with O12 as well. That's why we like add those two together, unlike we did for our first case here. And then similarly, if you think about DL by DX13, DX13 is only getting convolved with this value here. So you will get DL by DO12 since it outputs O12 like there, and then we will multiply this by F12. Okay. So like going back to fourth pass sometimes helps. So there you go. And then now, like, believe it or not, even this can also be represented as a convolution operation because DLDX can be represented as like a full convolution between 180-degree rotated filter F and loss gradient DL by DO. So first let us rotate the filter F by 180 degrees. This is done by flipping it first vertically and then horizontally. So we will have like this nice looking filter here. And then now if we perform a full convolution between its flipped filter F and DL by DO by like sliding one matrix over another from right to left, bottom to top, it generates a value of DL by DX just like how we discussed on the board just now. So to sum up, backpropagation is like convolution. Backpropagation and convolution can be explained by using the idea of convolution again. So DL by DF is the convolution between input X and loss gradient DL by DO, and a loss gradient with respect to the output O from the next layer. And DLDX is the full convolution between flipped filter F and again DL by DO. You just have to perform this operation from right to left until you reach to the end or the very first layer. I know that was like quick and very nasty, but like it really helps you a lot to just like chug it through. So we'll be recording this session. So if anything's unclear, just go back and try to like do the computation just like I did like on the board. So hopefully that will help. Any questions? Yeah?
Can you go back a couple slides?
Wait, sorry. Which one?
Oh, yeah.
This one?
So on the board, you have written that DL by DX12 equal to DL by DO11 F11, and it's slightly different on the slides. So which one is correct?
Which part? Which one on the slide is different?
DL by DX12 equal to DL by DO11 F11. On the slide, just integrate 1 or 2.
Sorry, I'm lost. The what? Point of memory.
Whatever is in the slide is in it.
Yeah. Oh, yeah. Sorry. My mistake. My bad. Sorry. Thanks for pointing out. Yeah, another question? No? Yep.
Could you explain like why we had to flip the thing again?
So it's like it's just to like help you transferring like the idea of backpropagation into like another example of convolution. Because if you think like convolution is an easy operation, right? You just like multiply, slide it down, and like add together, right? So in order to make that happen like an easy way, that's the reason why we want to flip the filters and then like do the convolution. You don't have to understand it that way, but I guess like that kind of helps you to understand and like make the use of idea of convolution again.
Can you think of it that this way that can you go to the next slide?
Mhm.
Oh, the next one. Yeah, this one. So like for dl by df, we are convoluting using the x, and for dl by dx, we are kind of trying to reverse it. That's why we are inverting the filter f as well.
I think I didn't get the question. Can you reiterate?
For dl by df, we are convoluting using the input x with loss gradient dl by do.
Right.
And for dl by dx, because we're trying to kind of inverse the whole process, that's why we're thinking of it as convoluting using the rotated filter.
So I think it's kind of confusing because we just like wanted to introduce the idea of convolution again in the explanation for backpropagation. That's why we kind of introduce like convolution and full convolution in this idea. So the reason why DLDF is just a convolution is because like we just have to like multiply and add together what we get from input x and loss gradient, right? So that's the reason why it's called convolution. But if you think about how we get to the value for DL by DX, like the operation itself, it's just like easier for us to like understand it if we call it as a full convolution. Full convolution, if you think about it, is different because we slide down the filter, like we slide down the input using this filter, right? That's like the difference of it. So convolution is just like a multiplication and then the addition. And full convolution means that you slide down your input with your filter size, and then you add it together. So that's like the difference, if that was your question. If we don't have any further question, we'll just move on to a fun part, which is code. So let's see here.
Hopefully it won't fall. Am I audible? Yeah. Okay, cool. Can you just... Okay, let's look at doing convolutional networks using PyTorch. This notebook is mainly for you all to go through like at your own pace, especially like the parts which are being mentioned here. It will really help you to do the homework too, and how you can use PyTorch for different things. I know there's been a lot of information today, so I'll just skim through whatever things are really important and should be focused on. Feel free to go through all, like, not feel free, do go through all of these things, all of these resources. It will really help you to understand what is happening and how is it happening. In PyTorch, it's basically we have, I'll go through like 2D and 1D image, 2D and 1D images, like what's the concept, like how do we mention the sizes which we just mentioned, how do we do convolution, how do we do all those pooling, how do we do upsampling and downsampling in PyTorch. So let's start with an image. Here the image, like we have defined a 3-channel 32x32 image. 32 is height, width, and so in PyTorch, important thing is the images are presented in the form of NCHW. N represents the number of images, C the channel, height, and width. Be sure of this thing when you will be augmenting or you will be using any other libraries, because some libraries follow NHWC format, and you might have to do permutations to change the channels and like change the shape of this image into NHWC, because sometimes having channels at the end help. So be cautious about what's the size and what's the dimensions of your image. We have an example of 1332, and for the 1D, we are taking 40 channels and 100 timestamped image. Not image, but like 100 times, 40 dimensional single for 100 timestamps. So again, in Con2D, this again is like that output, how to calculate the output width formula, and this is a floor. So this is automatically being done by Python by using that division, integer division in Python, but this is what's being done. And you use convolution 2D to define your convolution layer. So what is this? This is that input channels. So here you put an input channel 3 because you want your filter to have that input channel of 3. The out channels represents the number of filters here automatically. So when you define an out channel of 20, it will automatically create 20 different filters. Make sense? And the kernel size is 5, so it will be convoluting using 5x5 matrix. And there are other parameters like stride, padding. So stride is by default 1 and padding by default is 0. You can change it. So if you increase your stride, it will help you achieve the upsampling part and downsampling. And with increasing padding, you can play around with it to understand like what exactly output image you want, what size of the output image you want. Any questions here?
Yeah, I just wanted to ask if we have 3 input channels and 20 output channels, it means that we are having 20 kernels with 3 channels each.
Yes.
Okay.
Exactly. And that's why you see, if we use this convolution layer and pass our input image to it, we get an output of 120, 28 cross 28. 20, you can directly map it with the out channels. Why 28 cross 28? Do the maths. Kernel size 5, output like input width was 32 cross 32, right? Yeah. Anyone has any doubt how this 28 cross 28 can come, or you want me to do it? Cool, right? Cool. Okay. So this is nothing but just padding. We increase the padding, and here you can see, if I increase the padding to 2, I can retain the size of the image. So I again can get 32 cross 32. Input was 32, we got 32, we just increased the number of channels in our image. You can try this out, like this is different, just play around with different padding, what you want to do, how the sizes are changing, and like this should be so it should be like ABCD to you because when you do convolutions, these sizes, if you will try to re-implement any paper as well, these sizes is the thing which will matter. In fact, let me go through a good example. 1 second. Yeah, this example, here we got an output of 1 cross 20 cross 1 cross 1. It's very important. It will be really important to understand why do we we purposefully chose kernel size of 5 and then a pooling of kernel size with 28 to achieve 1 cross 1. And you can imagine that now these 1 cross 1 we can squeeze it to get a 20 vector of length 20. Why will we need it? Because some sort, we can add then that fully connected layers to it, because generally the entire network of convolution networks are we have convolution, various layers of convolution layer, pooling layer, convolution layer, pooling layer, and you finally add a fully connected layer to help us do that classification task at the end. So these things help, and you will have to figure out these kernel sizes when you will be doing your works again. What did I skim through? So these are different pooling operations. As I said, we have max, average, and you can just look through it. Different pooling, how to do different pooling things. There are also functions which are provided by, one thing I wanted to focus on this, This upsampling and downsampling, I've been talking about it a lot. Is there any doubt what upsampling and downsampling means? Oh, great, okay. So basically we have this nn.upsample function provided by PyTorch as well, which will help you to upsample an image from 16 to 32 using a scale factor of 2. If you want to use that formula of output size to identify how this 32 come, just imagine that this is a stride with 1 by, in this, the stride is equal to 1 by the scale factor, 1 divided by scale factor. Why? Because we are doing upsampling. So the stride, if you remember, it's in the denominator. It's 1 by 2, so we are multiplying it with 16 into 20 into 2. That's why it's getting 32. And for the downsampling, if stride is greater than 1, you can do downsampling, upsampling using direct convolution layers as well. Basically, you don't have to use this upsample function. We rarely use this. We directly use our convolutions and just add a stride, whatever stride we want to do, and just do upsampling and downsampling using con2D functions itself. Anything else I want to go through here? Okay, we have these convolutions functions as well, which like we don't have to create separate layers and pass the input through a layer. We can define f dot convolution in the functions itself, like f dot con2d, the image and everything, and it will give out the output. But it's always better to define the layers separately and like see how the network is progressing. So use that, like it's just good to know that these things exist, but usually you define different layers, and because then you have more scope of adding batch norm, pooling, dropouts, whatever you want to do across the layers. As I said, batch norm dropout, batch norm you must have used right now as well for homework 1 part 2s. It's helping you with that covariate shifts, and dropouts will give you that sense of ensembling. So you can add these in convolutions as well, and remember this is 2D. So we have con2D, so we are using batch norm 2D as well. And also a dropout version will be 2D. Be cautious of it. People tend to make mistake and try to use drop 1D, and then it won't work when you're doing convolutions 2D. This is basically, we are just reading an image. You can go through this drive, like connect to this drive and try it out. So, Backprop. On this image, we can do different transformations. Again, transformations will be really helpful. They help you do data augmentation, and especially for convolution neural, like computer vision tasks, transformations really help. So they are in the torch vision library, torchvision.transforms. There are various different transforms which are available. Check it out, like random resize crop. For example, this random resize crop will just randomly crop the image into like 100 cross 100. And there are other factors like how much randomness we want, and it will create more data. So it's used for data augmentation, and it helps in that solving the problem of overfitting, because convolution neural networks overfit very easily, and you will observe it very soon. So be sure, like this data transforms will be really helpful and very handy. Do apply it, do read about it, do read papers like what all data augmentation they used with that particular network which you want to use. All these things will, I guess, you will appreciate it more when you will play with your homework 2 part 2. But yeah, keep it in mind to come back to this and see how to implement data transforms. Cool. Let's look at an example.
Yeah, so before we finish, I just thought it'd be nice if I can show you guys like a really cool example of how CNN actually does the classification tasks. So I brought like an MNIST data example because like that's the most like accessible and like famous data set that you can use. So basically, MNIST data set is just like a handwritten numbers that you want to like classify into. So like the data set actually looks like this, and the task will be to classify these handwritten digits into the number that it corresponds to. So if you go through the notebook, it has all the details about how you can like prep the data, load it, and like all sorts of things. And here, I just want to like have some focus on the CNN definition that we made here. So here, just like you defined your network class for your homework 1 part 2, we are defining like our model class CNN. And here we are using like some convolution layers, just like Ashani has showed you guys in the previous part in the notebook. And then just want to address that in the in channels would be 1 because we are using our grayscale image, so we don't need to use the in scale of like in channels of 3. And then everything else I think is pretty self-explanatory, so you can just like go through by yourself. And then for the loss function, we use cross entropy. optimizer and all sorts of things. You can like take a look at it. And for like 10 epochs, I already did the training last night, which took about like 10 minutes to do so. And then as you can see, loss is like decreasing as it goes, right? And at the end, like if you evaluate the model on our test data set, I got 0.99 of test accuracy. So that's like pretty cool, right? And if you see like the 10 predictions from the test data, we have predicted our handwritten digits to have like these prediction numbers, but actually we had these digits. So you can see like some of the outputs that we got are a little different. Like for example, 5 and 8. This is also the mistake that I make, like writing 5 and then interpreting as 8. So maybe our CNN also did the same thing here. But I just wanted to show you guys how CNN could be used in real life in classification tasks, which you'll be also exploring in homework 2 part 2, where you'll be like playing around with classification and verification tasks on faces. So stay tuned, get excited, and I'll see you all guys like next week. Thank you for coming. Bye.